about polygons. We have lots of different polygons we can talk about, lots of different things we can do with polygons. And then we also have some special types of polygons, which we're going to talk about as well. The basic idea when we say polygon, or the underlying definition that we're dealing with, is many sides. That's not the most direct translation, but it's going to work for us here. What we're referring to here is something that has multiple sides to it. Now, in plain Euclidean geometry, the thing that we're going to focus on is this idea that we have to have at least 3 sides before we can have a polygon. We have 2 points. We can draw a line segment between those 2 points. We can label those as A and B, right? But that's not a polygon. Why is it not? Well, let's get there. Let's draw another line segment. We create A, B, and C. We now have 2 line segments drawn. We actually have an angle between them, which is, that we can measure in different ways, but the basic idea is what is the angle measurement between those 2 spots, right? But we still have a polygon. Now we have a polygon. What makes this a polygon? What's different between this and the previous 2 iterations of objects we did? We can also create something that looks, let's do something maybe like that. That wasn't intentionally made to look like a trapezoid. And we can maybe get rid of some of this, right? There. Now we have polygon. This is another polygon. Actually, it's not. Right here at the bottom. It's kind of hard to see on the video, but here, I'll overemphasize it. This isn't a polygon yet. Now it's a polygon. And I can label this as D, E, F, and G, right? So what makes these things polygons? Why was the first 2 iterations of ABC up here not a polygon? Why was the first iteration of D, E, F, G not a polygon? Well, the idea between this is that it has many sides. The second piece of this is that it's what we call closed. Now, when we say closed, what are we talking about? What we're referring to is, an easy way to look at this is that, like if we were going to fence in an area, can the sheep get out? Can the sheep get out of that space? No, they can't, because it's closed, right? There's nowhere for them to go. Can the sheep get out of this space? Yes. Or no. No, they can't, not unless they're jumping the fence, right? But what about that space? Can the sheep get out of there? Absolutely. There's a space right there they can leave from. It's not closed. We got to have a closed figure. So when we say closed, there's a whole definition that needs to go along with that. And that idea behind it being closed is that all line segments are connected to exactly one other line segment, or 2 line segments. Which is it? So we got this line segment, which we already use in A, B, C, D. So we'll call this M. We'll call this Z. How about this? We'll call this one K, L. We'll call this one P, and then I don't know, what have we not used yet? How about T? Going out of order there, right? Mess with your heads a little bit. MZ. What's so special about MZ? Well, it's a line segment, and it's connected to 2 other line segments. Exactly 2. AB. What's special about AB? AB is connected to exactly 2 other line segments. What's special about DE, or GF, or LP? Each one is connected to exactly two other line segments. And all line segments are connected in that fashion. And there's no line segment, like if there was this gap here where I put P, if there was still a gap there, then KL isn't, or rather LP, wouldn't have been connected to exactly 2 other line segments of that figure, right, to make it closed. So the idea behind it being closed is that every line segment is connected to exactly 2 other line segments. And the figure itself, by definition of being closed, is that all points, right, that lie on the figure on the edge of the figure are connected by some path. So if you think of this from a mathematical perspective, I should be able to stand here, walk all the way around without getting off of the trail and come back to where I started from. That makes it closed. Right? Another aspect of this is anything we put inside can't escape from the fenced-in area because it's closed. So a polygon is many-sided, and maybe a piece to this is that those sides are straight. All right? Sorry about the writing. So there are many straight sides, and it's closed. Now, we got these other pieces here, regular, convex, and concave. Well, let's start with concave. None of these are concave, which means they're all convexed. They're either one or the other. If something's a polygon, it's either convex or it's concave. Concave is a weird world. That's concave. Those are convexed. Concave means that if I were to pick, let me back up. Let's do the other definition. If I'm convex, it means I can pick any two sheep inside, any 2 points. All right? We got Sally the sheep, right? And Wilbur, right? Regardless of where these 2 sheep are inside the hexagon here, there are always the most direct path to one to the other. If one decides, I want to run over to Wilbur over here, the most direct path keeps them inside the fenced-in area. However, on the concave value, the concave one, I have, again, Sally and Wilbur that are in this pen. The most direct path is not going to take them straight through the enclosure. There's going to be this section that falls outside of it. It has a cave, if you will, inside the figure itself. You can't do this with a triangle, of course, but I'll leave it up to you to see how many of these other objects you can create that are convex. Can you do this with a quadrilateral? Which is actually the next stage of this is we have our triangles, because they're 3-sided. So we have our quadrilaterals, quad for 4, meaning they're 4-sided. Lateral meaning sides, right? And then we have pentagons, right? Gons for many sides, right? And then we have hexagons and on down the line. There are actually a lot of them that you can list. Normally, I only have the first 10 or so that I use. After that, it goes back to 11-gon, 12-gon. These are our shapes, and they come in convex and concave. Now, if it's convexed, we actually have special convex polygons. All right? We have special convex polygons that we call regular. They're a special one. Now, by definition of it being regular, it means all sides are congruent, all angles are congruent. Okay? All sides and angles are congruent. We have to specify sides and angles because triangles are the only one where one's going to force the other one to occur. Okay? Well, that's not true. There are other shapes where that occurs as well. But it's not true with squares, right? Not squares. It's not true with quadrilaterals. A square is a regular quadrilateral because it is the meeting, if you will, of a rhombus, which all the sides are congruent, and a rectangle, which has all the angles congruent. A square means all angles and all sides are congruent, and by congruent we're saying the same size and the same shape. So that's the idea behind those pieces. So once again, recap. Polygons are many-sided and they're closed. We have special types of polygons, convex and concave. Concave literally means that there's an indentation in the polygon. Convex means there are no indentions, right? Any 2 points, the line between those 2 points lies inside of the figure, right? And we have a special type of convex polygon, which is a regular polygon, right? And regular means that all sides and all angles are congruent. And we have to have both sides and angles. We have to have that discussion about both of those because a square is the overlap between a rectangle and a rhombus. Rhombus where the sides are equal. A rhombus where the sides are equal. A rectangle where the angles are equal. Otherwise, it's not regular. Some of the other figures, it doesn't really work out the same way, but those two it does. And there are ways of doing some of the others, like a pentagon. You can draw it in such a way that the sides are equal and the angles aren't. So, a lot of things going on there with that. Go through and discover what else, figure out what else you can discover about different types of polygons. Make sure you're familiar with the different names for their different shapes. And I'm also going to post another video that kind of links together the different types of polygons and how they fit together. I'm going to use a tree diagram to kind of build that up. But be looking through these definitions and understanding how these things relate to each other. Take care.